Welcome to the deep dive. We cut through the noise, get you the key insights from, well, stacks of sources. Today, we're diving into artificial intelligence. Now, we hear all the time about AI doing amazing things, art generation, self-driving cars, all that. But what's the secret sauce? The hidden ingredient? It's data. Yeah, AI, fundamentally, it's a learning machine. And just like people, what it learns, how it learns, even the biases it might pick up, it all comes down to the information it's fed and that dependency. It has some pretty surprising implications, actually.
Absolutely. So our mission here is really to peel back that curtain. We want to explore where AI's data actually comes from, why the quality of that data is just so critical,
Hmm.
and also how, biased or just plain incomplete information can lead to some really unexpected, sometimes serious risks. You'll get to sense not just of what AI is doing, but more importantly, why it's doing it that way and why that matters to you
Yeah.
in your apps and decisions that affect your life.
Okay, so let's unpack this learning thing. When we talk about AI learning, we're mostly talking about machine learning, right? This is where algorithms aren't explicitly programmed step by step. They kind of program themselves by looking at information. It's totally different from old school coding.
Exactly. It's a huge shift.
But how does that self-programming actually work?
Right, good question. So the most common approach is something called supervised learning. Think about teaching a computer to spot cats. You don't write rules like look for pointy ears. Instead, you feed it a labeled data set. There's just a huge pile of examples, maybe millions of photos, and each one has the correct label, cat, dog, whatever it is. An algorithm, like a sport vector machine, an SVM, gets trained on this. So for email spam, it might look at, say, 10,000 emails already marked spam or not spam. It converts the email text into what's called a feature vector, basically numbers, and learns patterns from those labeled examples to make predictions.
And the amount of data needed for the modern stuff, especially deep learning, it's just staggering. It's not really a coincidence that these powerful deep learning models like uh, convolutional neural networks or
Yeah.
the ones great at images, their rise happened right alongside this tech revolution we call big data.
Right, they feed on it.
Yeah, look at the ImageNet competition. That was a huge moment. It gave AI systems 1.2 million labeled images across 1,000 categories. That's just an insane amount of visual info for an AI to learn from.
And what's really fascinating, I think, is how much human effort is still involved, even with these self-programming machines. Those massive labeled data sets, they don't just appear. They're often built by, well, basically armies of human annotators. Think about platforms like Amazon Mechanical Turk. Real people are paid small amounts to click on pictures, label things cat or not cat, categorize text. They provide that crucial supervision signal. It really highlights this hidden human workforce behind a lot of AI.
That's striking. So humans are still kind of guiding the learning, even if indirectly. Okay, so once you have this mountain of raw data, maybe labeled by people, what's next? It can't just be about volume, can it? The preparation, how you organize it, that seems critical too, like an art form.
Oh, absolutely critical. It's definitely more than just feeding the machine.
How do machines even process complex stuff like, say, colors or sound?
Yeah, that's the trick. Raw data, an image, an email, isn't directly usable by most algorithms. It has to be transformed into those feature vectors we mentioned, numerical representations. So take something simple like colors. If you have categories like red, yellow, green, you might use a technique called one-hot encoding.
Yeah.
Basically, red becomes a vector like 1,000, yellow is 0, 1, 0, 0, 0. It turns categories into numbers the algorithm can actually work with.
Okay, that makes sense. But then comes the really interesting part, right?
Right.
The data splitting. You don't just use all the data at once. It gets divided, typically into three sets: training, validation, and testing. Why three?
Well, it's crucial for making sure the model actually learns and doesn't just memorize. You could have a really simple, dumb algorithm just store every single training example. It would look perfect on that data.
But completely useless in the real world.
Exactly. We need the model to perform well on new, previously unseen examples. That's the whole point.
So the training set teaches the basics.
Right. The validation set helps you tune the model's settings, its hyperparameters, without peaking at the final test data.
And the test set is the final exam and an honest grade on totally new stuff.
Precisely. And the splits vary, maybe 70% training, 15% validation, 15% testing is common. Or with really big data, maybe 95% training, 2.5%, 2.5%.
The goal is always to prevent that memorization, that overfitting.
And this whole careful splitting process connects back to this idea of getting unbiased estimators. So we usually don't know the true underlying patterns in the world, the real probability distributions. So we rely on these data samples, hoping they accurately represent that unknown reality. If your samples are biased or just not representative, your model's view of the world will be skewed from the start.
Which leads us right into the risks, the potential downsides. Because AI's reliance on data isn't just its strength, it's also where things can go wrong.
Definitely. The first big one is bias in the data itself. As the researcher Fei Lai said, if that data is biased, our machine learning outcome will be biased. And sometimes, she notes, the bias can have really serious, even fatal consequences.
Wow, fatal.
Well, think about medical AI or self-driving cars. But even less dramatic examples are everywhere. Barbara Gross pointed out how facial recognition often works better for, say, white men, upper income,
Why?
simply because the training data might have had way more pictures of them, uneven sampling. So the system literally isn't as good at recognizing other groups.
So your phone might not unlock easily, or worse, an algorithm screening job applications might unintentionally disadvantage certain people.
Exactly. Not because someone programmed it to be biased, but because it learned from biased data reflecting existing societal inequalities.
Okay, bias is a huge one. What else? You mentioned overfitting earlier.
Right, overfitting. This happens when the model learns the training data too perfectly. It picks up on noise and random quirks in that specific dataset, not just the underlying patterns.
Like memorizing the textbook answers again?
Pretty much.
Nice.
So it looks great in training, but fails miserably on new data. Imagine training a car recognition system only on, like, 10 specific 3D models from a video game.
It wouldn't recognize real cars very well.
Probably not. Or there's that classic, almost funny example.
Yeah.
An AI meant to detect animals in photos. Instead of learning what animals look like, it accidentally learned that pictures with animals often had blurry backgrounds in its training set. So it started identifying blurry background as animal. Yeah. It learned a statistical correlation that was totally irrelevant. That's overfitting. It explains why sometimes your recommendations feel stuck or search results seem off.
Okay, so bias, overfitting.
Yeah.
What else lurks in the data?
Then you get into something quite alarming: adversarial attacks. This is where researchers found you can make tiny, often imperceptible changes to an input like an image that completely fool an AI.
Imperceptible. Like, I wouldn't notice it.
Often, yes. Think subtle patterns added to eyeglasses that make a facial recognition system misidentify someone with high confidence. Or small stickers placed on a stop sign that trick a self-driving car's vision system into seeing something else entirely.
Worrying.
It is, and it raises a really fundamental question. If these systems, these neural networks, can be fooled so easily by things humans don't even notice, are they really learning or seeing like we do?
It sounds like something very different is going on under the hood.
It strongly suggests that, yeah, it highlights a major vulnerability, especially for systems where we need high levels of trust and security.
Are there other data challenges too?
Oh, sure. Things like imbalanced data sets are common. Like in fraud detection, you hopefully have way more genuine transactions than fraudulent ones. That imbalance can make it hard for the AI to learn to spot the rare cases.
How do they deal with that?
Various techniques, sometimes oversampling the rare cases or undersampling the common ones, or using algorithms specifically designed for imbalanced data. And then there's just missing values gaps in the data. You either have to remove those examples or try to intelligently guess or impute the missing information.
So pulling this together, AI eats data, huge amounts of it, deep learning especially. But Andrew Nang said requiring so much data is actually a major limitation today. Why is that?
Well, it contrasts sharply with how humans learn, doesn't it? Yoshua Bengio made this point. We can't realistically label everything in the world and meticulously explain every last detail to the computer. That's just not feasible. Humans, even babies, learn incredibly efficiently from relatively little data. We generalize. We have innate structures. We do transfer learning, applying knowledge from one area to another. AI, not so much yet.
Right, we see that lack of generalization. AlphaGo was amazing at Go after training on millions of self-play games.
Equivalent to centuries of human play.
Yeah. But then, try to get it to plan a slightly smaller Go board or a different shape. It completely failed without retraining from scratch.
Or DeepMind's breakout player.
Yeah.
Superhuman scores. But shift the paddle up just a tiny bit on the screen.
Performance collapse.
Exactly. These systems are often brilliant, but incredibly brittle. They master the specific task they were trained on, but struggle with even minor variations.
That doesn't feel like real understanding.
It doesn't. And a great illustration of this gap is something called Bongard problems.
What are those?
They're visual puzzles. You see two sets of simple diagrams, say 6 in each set. You have to figure out the abstract rule that distinguishes set A from set B. Humans can usually solve these with just those 12 examples. It requires abstraction, analogy.
Okay. And AI.
Well, researchers tried training state-of-the-art ConNets on a similar task, using 20,000 examples. The result,
Okay.
the AI performed only slightly better than just random guessing.
Wow, 20,000 examples versus 12.
It powerfully suggests that even with vast data, current deep learning methods lack those fundamental human abilities for abstraction and analogy. It's led critics like Judea Pearl to argue that AI needs to move beyond this purely data-centric philosophy to achieve more general intelligence.
So, reflecting on our deep dive today, we started with AI's hunger for data, these huge labeled data sets, often built with lots of human effort. We saw how crucial data quality and preparation are cleaning, transforming, splitting it just right. But we also uncovered these real dangers, bias creeping in from the real world, models overfitting and failing to generalize, and even these weird adversarial attacks that show how different AI perception might be from ours.
Yeah, it really comes down to this. Data is the lifeblood of today's AI. It fuels everything. But it's also its potential Achilles heel. The quality, the fairness, the robustness of any AI system, it all traces back directly to the data it learned from. So maybe a final thought to leave you with. Human learning, human knowledge, it seems so tied to our built-in cognitive abilities, our experiences, allowing us to learn broadly from limited examples. AI, right now, mostly relies on this massive feeding of external labeled data. So what's it actually going to take for AI to bridge that gap? To learn about the world, truly understand it like humans do, not just learn from patterns in data? What kind of data or what kind of fundamental learning breakthroughs are needed to move from just statistical pattern matching to something close to genuine comprehension?